So next topic I wanted to introduce then was say a few general words about least squares fits, and then be explicit about a least squares fit to a straight line and the equations describing the best fit to a straight line. And there'll be equations for the two parameters associated with a straight line, right? The slope of the straight line, the intercept of the straight line. So basic idea of a least squares fit is it's a procedure, and there are actually other procedures for finding the best curve through some data points. And it's done for a least squares fit. It's done by minimizing the sum of the squares of the differences between the data points and the fit function. So I've tried to show that on this plot over here on the left-hand side. So I'm imagining some dependent variable x. I'm imagining some imagining some independent variable x, some dependent variable y, and some data points, some x and y values. So x1, y1, x2, y2, so on and so forth. So I plotted those points, and I'm imagining trying to find the best curve, or in this case, best straight line through those data. That's the dashed line here. And in least squares fit, what we do is we compute the residuals between each data point and the function. So for point number one, that's the residual is this vertical line here, distance between function and data point. For point number two, the residual is this straight line here, distance between data point and function, and so on and so forth. So we compute those residuals, and then we square them, and then we sum them, and that's what we call the chi-square, the sum squares of the residuals, and we try to minimize that chi-squared. We try and that sum of the residuals squared as small as possible, and that's going to define our best curve, or our best straight line through the data. So that's the basic idea. A few more comments on that. So one thing we don't do is just sum the residuals and minimize that. We sum the squares of the residuals and minimize that. And the reason is, if you sum the residuals, right, some residuals are going to be positive, some residuals are going to be negative, depending on whether the data sits below the function or above the function. So if you just sum the residuals, you get lots of cancellations between positive and negative residuals. And the sum of those residuals would not be effective in finding the best curve. A second thing we don't do. So you could imagine, well, I won't sum the residuals because of the signs. I'll sum the magnitudes of the residuals. And that would work to find a best curve through the data, or a best straight line through the data. But it's sort of mathematically, computationally more awkward. And so that's what leads to the idea of summing the squares of the residuals and minimizing that sum of squares of the residuals, what we call the chi-square. And so that's this formula down here. On the left is a notation, the chi-squared. On the right-hand side, inside the parentheses, you see the data points yi, so the dependent variable. You see the model for the data points, the function x of I, so the prediction for the data points, you see the calculation of the difference, so the residual between the two, and that we're squaring it and that we're summing it. And so that's the chi-squared that we're going to minimize. So this on the left-hand side is just a picture of that chi-squared for the example of a fit to a straight line. So if you're fitting a straight line, your fit function has two parameters. It has the slope and an offset. I call them M and C here. And so chi-squared is a function of the fit parameters, and you're trying to minimize the chi-squared to obtain the best values of the fit parameters. And so I'm showing or picturing that in this plot here. So horizontally, I'm varying the slope parameter M. Vertically, I'm varying the offset parameter C. And so the two-dimensional plot is kind of this space, this world of different values of M and C. And in that space or world of different values of M and C, you see kind of like a landscape, a contour landscape. And what we're actually looking at here is a deep well or valley. So the walls of the valley go up through these different colors towards the top right and towards the bottom left. And right here in the center of the plot, this is the minimum chi-squared. And so that minimum chi-squared defines a certain value of the slope, about 0.9, defines a certain value of the offset, about minus 4.8. And so those would be the best fit values that we're trying to find. And so that's our goal, to minimize that chi-squared, extract the best M, best C. And so here's the math of obtaining the best value of the slope, the best value of the offset from the chi-squared minimization. So this little sequence or this little argument or derivation here starts from a definition of the chi-squared and what we want to minimize. So that's the first line. And through these steps, it works down to this little matrix equation here. If you look over here on the left-hand side, the equal sign, then the elements of this two-element vector are the best fit slope M, best fit intercept C. So this is what we've derived from minimizing the chi-squared. And for the straight line case, the procedure's fairly straightforward to write down and to derive by hand, right? So when we minimize the chi-squared, at the minimum of the chi-squared, the variation of the chi-squared with M is going to be 0 because we're at the bottom of this well. And the variation of the chi-squared with C is also going to be 0 because we're at the bottom of this well. And so the first thing in the derivation I do is take the partial derivative of the chi-squared with respect to M. And so I just differentiate this quantity with respect to M here inside the square. And then I do the same thing for the chi-squared with respect to C. I differentiate the chi-squared with respect to the variable C. So here it is also in the square. And then I'm going to set those two derivatives to be 0 over here on the far right, because that's where the minimum is. So this is defining the minimum. And you can see, right, when inside the summation, right, when I differentiate with respect to M or differentiate with respect to C, I'm going to lower the power by 1 of this function of M or function of C. So you see that in this parentheses here. and in this parentheses here, you get out a factor of 2. That's the factors of 2's up front. And you get out the you get out a derivative of the quantity inside the parentheses when you differentiate with respect to m. That's where the xi comes from. And when you differentiate with respect to c, there you're just going to get a -1 factor. So we get these two equations here. And at this point, we can, cancel out this common factor, 2m or 2c, in the two equations. And we just have statements from these partial derivatives that this summation upstairs here and this summation downstairs here over the data points is equal to 0. And that allows us to solve for m and c. If you think of those equations, we got two unknowns, m and c, in those equations. We can rearrange those two equations for those two unknowns to solve for those two unknowns. And that's what's done down here. It's done in matrix form just because it's kind of convenient to do it in matrix form. So this first row of column vectors and matrices here is just me rewriting these two equations in the form of this matrix equation, single matrix equation. So it's nothing other, this top equation here, nothing other than rewriting the two partial derivatives. You can see probably that if you take this column vector MC and you multiply the top row of this 2x2 matrix, that gives you the terms, if you check it, that are in the first partial derivative. And if you multiply the column vector with M and C, multiply the bottom row of the matrix, you get the second partial derivative. You get terms in that. And so that's where this equation comes from. And then if you think about it, if you multiply the left-hand side and the right-hand side of this equation by the inverse of this matrix, then it will cancel out the matrices on this side of the equation, leaving just M and C, because we multiplied by the inverse of the matrix. And it will leave us on the right-hand side with this expression here. And so this is how you derive the best fit values of M and C from the idea of minimizing the chi-squared and the procedure of calculating the partial differentials with respect to the slope and the offset of the chi-squared. I'm not going to go through this slide in gory details, but I want to show you the results of this slide. These are the results for several things. So sigma y squared, so this is the square of the standard deviation of y. This is the variance of y, where y are the dependent variables, the data points. So I said the problem that I'm solving is straight line fit to a set of data points where the uncertainties are equal to one another, and actually the uncertainties were not specified. I didn't say what the uncertainties were. Rather, we can calculate the uncertainties from the data. And so this top equation here is kind of a starting point on the uncertainties. Based on the best fit values of M and C, we can calculate the uncertainties, the uncertainty on the data points, which are all common uncertainties, from the data points themselves and the best fit values of M and C with this little equation here. What you'll recognize here is that this guy is nothing other than the chi-squared. So this on the inside, the summation is the chi-squared. And so that is a measure of the squared deviations of the data points from the best fit curve. If you divide it, supposing you divided it by the number of data points, then you might think, well, you'll get the average deviation or square of the deviation from the best fit curve. And that would be, the variance or the square of the standard deviation. And so that's how I'm calculating the variance or the square of the deviation from the chi-squared using the best fit values of M and C. It's actually divided not by n, though. It's divided by m minus 2. The reason for the minus 2 is that you've calculated two quantities from the data. You calculated M and C from the data. So there's not really n degrees of freedom left in this data set. There's n less 2 degrees of freedom left in this data set. And so that's why we divide by not n, but n minus 2 to calculate the variance of the data points. You could imagine that, supposing you just had 2 data points. Well, obviously, if you've got a straight line, you can put it through both of those data points exactly. It wouldn't make sense to be able to calculate an uncertainty from that because you're not sensitive to it. And this factor here says that it would be nonsense to do this for n equals 2. Okay, so that's just to point out that once you got your best fit straight line, you can simply compare the function with the data and estimate the uncertainties on the data. We didn't know them from the measurements of the data. We just calculated them based on how much they fluctuate around the model. Once you got the sigma y's, you can use those, and I use them in each 3 of these equations here, to calculate 3 other variances here. Actually, the first 2 we would call variances. The last one is called a covariance. So sigma m squared is the uncertainty, is this square of the standard deviation, or the variance on the slope. Sigma c squared is the variance, or the square of the standard deviation of the offset. So these 2 guys in the center here, these tell us how well we've determined, how poorly we've determined the slope and the offset. The way we've calculated them is basically using the rules for propagations of uncertainties. We've got an uncertainty in sigma y, in the data points. So that's the sigma y squared here. And I'm just propagating them to uncertainties in the slope, m, or the offset, c, by multiplying these variances of y with the squares of the partial differentials of the slope with respect to y and the offset with respect to y. So the partial differential of the slope with respect to y would be big if the slope is really dependent on y. And so that would give us a bigger error. If the slope was only slightly dependent on y, that would give us a proportionally much smaller error. And so these partial differentials tell us the relationship or the sensitivity of the slope and the offset to the uncertainties in the data points themselves. So that's all that's going on here. Propagating errors by standard procedures for propagating errors. And if you do that propagation, I didn't calculate this, obviously, these are the 2 equations. They're starting to look messy. There's one last thing I'll just comment on. This guy here, sigma subscript mc squared. So that's what we call the covariance between m and c, between the slope and the offset. This thing measures the correlation between the slope and the offset, between the parameters m and c. So if that correlation, supposing it was 0, supposing we found it to be 0, that would say that if you change c you don't tend to change M. If you change M, you don't tend to change C. That's uncorrelated. If we found that this quantity was not zero, then it would be saying that if you change the slope, you'll tend to change the offset, and vice versa. So this measures a correlation between the M's and C's, and we call it a covariance or a correlation coefficient. And again, it's you can calculate it from these partial differentials. Now you need to know both how C changes with the data points and how M changes with the data points. So it's a slightly different calculation, but it's the one that tells us the correlation between the two. And again, I haven't derived it. Here's the result in terms of the error on the data points.